All right, everybody, welcome back. 7.2 Properties of Exponential Functions. We're going to first open up here. This is the same question we did in the previous lesson. However, I'm going to show you an alternative method that I spoke about. I used substitution the previous time. This time we're going to solve them both for a and then set them equal. So we'll check this out here. Remember, the form for an exponential equation is y equals ab to the x power. So we're just simply substituting x and y in to create our system of equations, and then we'll solve using equal values method. Okay, so 8 equals ab to the fourth, and 32 equals ab to the sixth. Now we're going to solve both of these for a because that seems to be way easier to solve for. And same thing here, divide by b to the sixth power. And I get 32 over b to the 6th equals a. And since both of these are solved for a, then I can just set these two equal to each other and solve. Okay? So I'm going to set my a's equal to each other. And then I'm just going to cross multiply. All right, divide both sides by 8. Then divide by b to the fourth. We get b squared equals 4, and then we square root and we get b equals 2. Okay, now it doesn't matter where we plug b in there or there. Okay, substitute that back in to solve for a. Okay, 8 over 2 to the fourth power, that's 8 over 16, which is 1/2, 0.5, that's your a value. And then substitute a and b back into your originals to write your final equation. Y equals a, which is 0.5, times b to the x power. All right, and there's your final equation. Once again, we could type that in our calculator and confirm that our 2 points up here, 4, 8, and 632 are in fact in there. Okay, so just a quick review there. Make sure you know how to do this process. It will show up again on assessment, guaranteed. Okay, so let's just continue working with some exponentials, just reviewing initial value times the multiplier raised to the time, and then we will talk about half-life and compound interests. Okay, so you get $1,000 for your 16th birthday. Instead of spending the money, you decided to put in an account that earns 5% interest each year. How much money will be in the account when you turn 25? Okay, so set it up. Initial value is $1,000. Okay, your multiplier, if you're earning 5% interest, okay, that's 100% plus 5%, which is 105%. Move the decimal 2 places, we get 1.05. Or you could just take 1, which is 100%, plus 0.05 to get your 1.05. Okay, now when we put this to our time, okay, we have to figure out, okay, I got this when I was 16, now I'm 25, how many years went by? 9 years, so we raise it to the 9th power. Okay, and then we just jam in our calculator to evaluate. So we have 1,000 times 1.05 raised to the 9th power. Okay, so $1,000 turned into $1,551.33. Okay, let's try another one. Okay, now we bought a 2010 Jeep Wrangler, purchased for $34,000 and is depreciating, which means losing 18% annually. Write a function that models the value of the Jeep at any time after it was purchased. So our initial value is $34,000. Our multiplier, okay, we take 100% minus 18%. Okay, that gives us 82%. Move the decimal, we get 0.82 as our multiplier. Okay, and then we raise it to X number of years after 2010. Okay, make sure we are aware of our initial value was 2010. Okay, what's it worth in 2020? So we just substitute the difference in years, so it's 10. So 34,000 times 0.82 to the 10. and the value of our Jeep is $4,673.23. Okay, make sure you have your unit of measurement in there. Okay. All right, so these two questions here, again, talking about money and investing. We're going to get a little bit more detail with that here in the next couple of slides after half-life. But make sure you always have your unit of measurement there. Okay, we talk about bacteria, money, okay, the number of this, number of that. Make sure you always have your units when answering a word problem. Okay. All right, so half-life. All right, half-life is, okay, the time it takes for half the substance to decay. So that's essentially what that means. So how long did it take before half of it remains? Okay, which means half of it disappeared. All right, so it's kind of the same setup. A sub 0 is still your initial value. Okay, that's your initial value. Your multiplier for half-life will always be 1/2 or 0.5. Okay, because we're losing half. Okay, which means half remains. All right, now up here, your exponent. Okay, some people write this exponent as x over h, which that's essentially what that is. It's x is the time in units, the same as your half-life units, and then h is actually the half-life. How long does it take for half of it to disappear? Okay, so we'll do a couple questions here. And again, the exponent up here is just the adjustment of your time. Okay. So let's take a look here. A radioactive element has a half-life of 1 hour. Okay. Write a function at miles of decay if you started with 100 grams sample. So y equals, our initial value is 100, our half-life is 1/2. Okay. And we're going to raise that to the x power. Okay. So it's x number of yeah, we put x over 1, okay, because this is every hour. Okay, now we don't have to put the over 1 because our time is hours. Okay, if we have to adjust our time, we can do that accordingly. All right, so how much is left after 5 hours? You just simply plug a 5 in. And we get 3.125. And our units are grams, so make sure you have grams. All right, how much remains after 2 days? Okay, well, our time up here is in hours. Okay, so 2 days is the equivalent of 48 hours, right? So that's going to be our exponent. So 100 times 0.5 raised to the 48, and that's a very, very small number. 3.5527 times 10 to the negative 13th power grams remains. So practically nothing. Okay, that might be immeasurable, but you're always going to be left with something. It's never ever going to disappear. It's always going to be a small trace because half of it disappears, which means the other half will always remain. Okay, here's a question for all you coffee, soda drinkers out there, tea drinkers. Caffeine has a half-life of 5.7 hours in the human body. Okay, so if you drink a Coca-Cola at noon, how much caffeine is going to be in your body when you go to bed? Okay, so there's a couple things we need to know. How much caffeine did we start with? Okay, we need to know the initial value of caffeine. And we also need to know what time to go to bed. What time is bedtime for you? Okay, so we might all answer this a little bit differently because we all might go to bed at different times. Okay, so what time do you go to bed? I try to be in bed by about 10 p.m. Some of you might be earlier, some of you might be later. We're going to use 10 p.m. for this example. Okay, so if a 12-ounce can contains 32 milligrams of caffeine, okay, so we drank all that, so that's our initial value. 32 milligrams of caffeine times half-life. Okay, now here's where we have to adjust for this. Since the half-life is every 5.7 hours. Okay, that's going to be the denominator of my exponent. Okay, how many hours went by from the time we drank it to the time we went to bed? Well, noon to 10, okay, was 10 hours, right? So that's your exponent. So when you type this in, this exponent has to be in parentheses, okay? Now on these calculators here on your iPads, everything you do up there stays in the exponent, which is kind of nice. Okay, if you're just using the regular TI-83, you would have to put that exponent in parentheses, otherwise you're getting a wrong answer. Okay, so we actually have 9.48 milligrams of caffeine. So if you drink that at noon and you try to go to bed at 10 o'clock, maybe that's why, because you still have maybe a large amount of caffeine in your body that's keeping it from shutting down. Okay, here's another one. Okay, a certain particle created by a high velocity collisions at the CERN super collider has half-life of 6.2 milliseconds. Okay, find the amount of this particle that remains after 1 second. Okay, if 250 grams were created upon impact. Okay, so we have our initial value of 250 times half-life, 1/2. Okay, now we have to raise this appropriately. All right, your half-life is 6.2 milliseconds. Okay, we're asking for 1 second. So how many milliseconds are in 1 second? Okay, there's 1,000. Right, so there's 1,000 milliseconds in that 1 second right here. Okay, whoops. All right, so that's what we type in. And this is a very, very small number as well. 6.99 times 10 to the negative 47 grams. I'm looking for our unit of measurements. Okay, without that unit, you're probably going to lose a half point. All right. All right, this last one here. Okay, this is a little bit different. Carbon-14 has a half-life of every 5,730 years. What percent of the original amount of carbon-14 would you expect to find in a 20,000-year-old sample? Okay, so for this one, you could pick any value as your initial value. I like to use 100 because it's easy to find percents there. So I'm just going to make it up and say, okay, I have 100 milligrams or grams, whatever. All right, doesn't matter what number you use. We could always come back and compare to it. All right, multiplier is 1/2. Okay, and the half-life is every 5,730 years. We want to know how much is left after 20,000 years. Okay, so if I crunch this number, okay, I get 8.897 grams left. Now if we compare the amount that I ended with, which is this, and divide it by the amount that I started with, okay, we get 0.0897, which is 8.897%. Okay, now I'm going to show you here that it doesn't matter. Say we pick 5 as our starting value. Okay, everything else stays the same. Right? Right, and this time we get 0.44489, blah, blah, blah. Okay, if we take that answer, the 0.44489, and divide it by what we started with, which is 5, okay, we get that exact same decimal. Okay, from that line to that line, okay, that is 8.897%. Okay, so we can get it with regardless of what starting value we pick. If we're comparing a percent, okay, it's part of it divided by the whole thing. So there it is. Okay, so there's half-life. Okay, we saw a couple examples where everything was straightforward. We saw some where we had to adjust the time, just like this one here, because half-life wasn't every 1 day or 1 week or 1 hour. Okay, it's every 5,730 years. So that's how we adjust for our time up there. Okay, now the next one, Okay, if anyone plans on having any money in the future, okay, you're probably going to invest it. And when you invest it in a bank or stocks and bonds or whatever, okay, you're going to earn interest on your money. That's essentially free money. Okay, so here's the interest formula. Okay, it looks big, ugly, and scary, but again, everything comes back to initial value times the multiplier raised to the time. This formula does a very nice job of actually adjusting all of those things for you. All you have to do is plug in appropriately and then type in your calculator appropriately. Okay, so A is the amount that we get out. Okay, P is your principal amount or your initial amount. Okay, same thing. Okay, what's in parentheses here, all right, that is building your multiplier. The 1 is already your 100%. Okay, the important thing here is when you type in your rate, okay, when you plug in up here for your rate, that rate needs to be a decimal. So if it's 5%, you don't put a 5 there, you put in 0.05. Okay, if it's 10%, you put 0.10. Okay, and then N is the number of interest periods per year. So if you can see the slide below it, you know, say we'll go monthly. Well, that means you're compounding your interest 12 times, once every month. So N would be 12. All right, and your exponent then, we have to adjust for that as well. Okay, that's to the NT power. Okay, so it's the number of interest periods times the number of years you need it done. Okay, so here's a little cheat sheet. Regardless of what the problem gives you, annually means once a year, semi-annually twice, quarterly is 4 times a year, monthly 12, bi-monthly is twice a month, so that's going to happen 24 times. Bi-weekly is every other week. Okay, so that's 26 times it happens throughout the year. If you're getting your interest compounded weekly, that's 52 weeks in a year. And obviously daily is 365 days. Every day you're getting your interest. Okay, the more times you compound your interest, the more money you're going to make because you're going to earn interest on your interest. Okay, that's why it's nice to continually invest money and then don't touch it. Okay, because you're going to continue to earn on that. Okay, so we'll do some examples here. Okay, and hopefully some of you might turn into some very wise investors in the future once you see how your money grows without even touching it. So you have an account that returns 5.5% annual interest compounded monthly. Okay, don't just look for that percentage. You have to read to figure out that right there, monthly. If you invest 25 grand for 15 years, how much money's in your account? Okay, so same idea. Your principal or your initial amount is 25,000. Now let's build your multiplier. You get 5.5%. Okay, remember 5.5%. We get rid of the percent, it's 0.055. A lot of people put a 1 here. Do not do that. Okay, your 1 is already here. Okay, and because it's monthly, that's 12 times per year. And then we raise it to 15 years times 12 months. So because this is monthly, we need to convert this to be monthly. Okay, like I said, the formula converts everything for you as long as you plug in appropriately. Nothing left to do other than to crunch the numbers. So let's see how much money we got. 25 grand times 1 plus 0.055 divided by 12. And that's raised to the 15 times 12 power. Okay, let the calculator crunch the numbers for you. So you just turned 25 grand. Okay, you more than doubled it. Okay, we now have $56,939.59 in that account. Okay, that's why you invest your money. All right, so if you got extra money laying around, don't know what to do with it, invest it. Okay, because it's you earn it. All right, it's better than digging a hole in your backyard and letting it sit. 15 years, you dig it up, you still got 25 grand. You invest it wisely, you can earn a lot, you can make a lot of money. Okay, here's another example. You have an account that returns 7% annual interest compounded daily. All right, 365 times a year. If you invest $1,500 for 10 years, how much money do you have in your account? So, initial value times your multiplier. Let's build it. 7% is 0.07. How many times a year? 365 times. So you don't get 7% each time. It's 7% throughout the year. Okay, so you get a small fraction of that percentage per day. All right, raised to 10 years times 365 days. So because this is daily, This has to be daily, which is why we're multiplying by 365. So if we crunch the number, 1500 times 1 plus 0.07 divided by 365 raised to the 10 times 365, $3,020.42. So once again, some of you might be like, oh, whoop-de-doo, 10 years, I maybe could have used that 1500. Okay, well, what if it was 15,000? Okay, you can continuously add money to your investments, but this is just the compound interest formula. If you put that amount of money in and you don't touch it, that's what you get out after 10 years. All right. This question here, okay, you could answer a couple different ways. You could actually crunch the numbers, or you could just answer it according to what you know about how things are compounded. Let's read it here and then we'll discuss. You can choose to invest $5,000 into one of two accounts. The first compounds quarterly at 7% interest. The second account compounds daily at 7%. If you plan to invest the money for 20 years, which account should you choose? Well, because these interest rates are the same, okay, you want to go with the one that compounds it more frequently. Okay, so you're going to choose the daily account. Now, let's actually crunch the number just to see a comparison of the two. All right, so we have $5,000, so this will be the quarterly one. And we'll do the daily one over here. So $5,000 times 1 plus 0.07 over 4, and that's 20 years times 4 times a year, so quarterly. So we got $20,031.96. Okay, if we do it daily, 365 times a year, so we got 20 years times 365 days a year. So that is $20,273.27. So you might be thinking, okay, well, it's a difference of $143 approximately. Okay, what's the big deal? Well, if you invest it for 40 years, what would that $173 turn into? Okay, my take is on it, the more money the better, and it's free, so why not maximize your profits? Okay, whether it's pennies, whether it's dollars, thousands, doesn't matter. It's free money, and I'm going to take it because I invested wisely. Okay, so a few examples there where we compounded quarterly, daily, monthly, weekly. Okay, just make sure you pay attention to everything in the question. Don't just look and see 7% and say 1.07. Okay, make sure you're reading and analyzing and then plugging into the compound interest formula appropriately. Okay, very important. Okay, the last thing here, okay, that we're going to do is a continuously compounded. Okay, which means it's compounded always, all the time. Okay, we don't have to wait and say daily. Okay, if we're comparing daily and quarterly like the previous question, I'm going to go with daily. If we're comparing daily and continuously, I'm going continuously because it's continuously earning money, just like it says. Okay, so in order to do that, we're going to use the natural function here. Again, this is just definitional stuff. Okay, it's on your calculator. This isn't anything you have to memorize. Okay, the exponential function with a base e are very useful in describing continuous growth and decay situations. Okay, so this is how e is actually calculated, which is kind of above our level right now, but we're going to use it. Okay, so e is approximately 2.7 blah blah blah, and again e is right here. You have to hit second and then ln, e to the x. So if we do e to the first, that's where that number comes from. Okay, this number here is that number there. All right, so the natural exponential function f is defined by f of x equals e, the number for every x. And again, just very useful in solving real world modeling applications where things are continuously, whether they're continuously growing or continuously decaying, things don't just happen, oh, the hour went by and bang, now we're down to this. It's continuously happening over time. Okay? So, how are we going to use this formula? Okay, so here's our formula. Oops. A equals PE raised to the RT power, excuse me. Okay, so continuously compounded interest formula. A is your total amount, okay, so that's the amount of money that you earn. Okay, P once again is your principal amount or your initial value. Okay, when they talk money, they say, oh, what's your principal? Okay, no, it's not Dr. Bowman. No, it's the initial investment that you put in. Okay, once again, when we look at this R has to be your interest rate as a decimal. So if it's 5%, it's 0.05, not 1.05. Don't convert it to a multiplier. It is as a decimal. Okay, and then T is the number of years you actually want to do it. Okay, so let's see how this actually works. Okay, an initial investment of 35 grand is continuously compounded. Again, the importance of reading the problem. At 8.5% interest. How much is it worth after 5 years and then 15? Okay, so we'll do our 5 years here. We'll do our 15 years over here. So 35 grand is your principal or initial value. E raised to the RT power. So our rate is 8.5%. So take that decimal back 2 places. 0.085 times, okay, how many years? 5 years. Okay, so let's see what 35 grand did in just a 5-year investment. E to the 0.085 times 5 power. So all that's raised to the exponent. Again, if you're using just a regular calculator, you have to do E, insert a left parenthesis, and then do that calculation inside parentheses to make sure it's all the exponent. Okay? So in just 5 years, your 35 grand turned into over 53,000. Okay? So what's it going to do for 15 years? Okay, again, all that's raised to the exponent. So we'll change this to be 15. Now our 35 grand turned into $125,254.55. Okay, not bad. Okay, not many people have 35 grand laying around to invest. However, if you do, okay, tuck it away, invest it. Now 8.5% is a pretty high interest rate these days. However, you can still get into some stuff that does yield you those percentages. So once again, if this isn't a lesson on math and how the numbers work, maybe it's a lesson on saving money, okay, which is also extremely valuable. Okay, but every question we've done, previous lesson and this lesson, everything comes back to initial value times your multiplier raised to the appropriate time. Okay, now some things we have to adjust. Okay, and we did that with the formulas, the special formulas, or we kind of shifted gears and went to the continuous approach. But again, we have to read the problem before we start plugging numbers into formulas. Okay, the last thing we're going to talk about, we're not going to spend a ton of time on this, is graph shifting for an exponential graph. Okay, exponential graphs are a little tricky because the HK, normally HK was our locator point for everything. However, that is not true anymore. Okay, yes, your graph still shifts horizontally by the H value and vertically by the K value, but if you plotted HK, that's actually not a point on the graph. Okay, and the reason is because of this. The K value is a horizontal asymptote, so that is actually a dotted line that you cannot cross. All right, so when we talk about the locator point, okay, highlighted here in yellow, it gets kind of tricky because the A value plays a factor, and then the direction, if the A value is negative, that flips the whole thing upside down, and then it's then we're shifting to our horizontal, everything's below the horizontal asymptote, so we're going down one from that. Um, in talking to a lot of math teachers and discussing this, okay, the best way to do this is just to create an XY table, okay, whether you do that by hand and just crunch the numbers, or whether you have a graphing calculator, punch it in, plot the points appropriately, and then, always clearly label your horizontal asymptote, okay? So if we look at some of these graphs here, okay, our A value still tells us everything, okay, it's positive, so it's going to go up, it's going to go this way, all right? This value here tells us it's increasing, okay, and then this one's not shifted at all. So if we just type this in, 4 times 2 raised to the x power, okay, and we looked at our table, okay, you're probably not going to get too many nice points, okay, negative 3.5, negative 2, 1, negative 1, 2, 0, 4, 1, 8. I think that's all we can graph, okay? So because there's plus 0 out here, we know the horizontal asymptote is going to be 0. So you would draw a dotted line there, and that's your horizontal asymptote. All right, so your graph is slowly increasing from here and then takes off. All right. So if we take all this, oops, let's try this again. That's not what I wanted to do. Where'd my line go? Now let's cut this out. All right, we're going to keep that up there just for a hot minute. Okay, now this one, okay, all this is a horizontal shift to the right too. All right, so we can hopefully grab this graph right here, which I can't do at the moment. I got to cut it out again. All right. Technical difficulties. Let's try this again. All right, I'm going to grab this graph. It was here. Okay, now I'm just going to shift it to the right too. 1, 2. Okay. So my other graph got shifted to the left just a little bit. Let me go back and redo all that. Okay. So again, if we look here on our table and we plot the points that we know, starting with negative 3, negative 2, 1, negative 1, 2, then, whoops, 2, then 4, then 8. Okay, we have our horizontal asymptote here. We're never going to go below that, no matter how far to the left we go. All right, if I take this graph, I copy it, and then I paste it, that graph is just going to shift right too. So 1, 2. Okay, so there's your second one. All right, same thing with this one. If we do this and we shift it right 2 and then down 3, okay, we're going to have the same situation. Put that graph up. Actually, we'll undo that for a second. So that's going right 2 and then up 3 from our original. So if I take my graph here that I had my original one, no, I can't get it. Okay, all those points are going to go right 2 and then up 3. So I'll try and change this to red. So right 2 went up 3. 1, 2, 3. 1, 2. so your graph's going to come down here, and your horizontal asymptote's going to be there. So -3 is going to be that imaginary line, okay, and then it's slowly going to increase and come up this way. Okay, once again, we could type all these points in here, all these equations in there to confirm everything, but the locator point is not as easy and convenient as all the other families of functions that we've looked at. Okay, so highly recommend knowing how to use your calculator or just making your own XY table and plotting the points accordingly. Okay, so any questions with this, we can analyze further in class in person and see what, a negative A value does. If it's -4, okay, I just want to show you this here real quick before we end it. Zoom standard. Okay, now it shifted our graph down. Okay, so it's the same graph, just reflected over the x-axis. Okay, so let me get rid of this one. Okay, so that's what our graph's doing. Instead of increasing, it's going down. Okay, so that's why the whole HK locator point thing is extremely difficult. All right, so give some of these problems a try. Hopefully you understand the new formulas. Again, the only thing new we covered today was half-life and compound interest formulas. So understand each part of that, the principal, the percentage, the multipliers, the decimals, and adjusting to the time. Okay, it's very important that your multiplier matches your time. Okay, and those formulas are designed to help you do that. All right, thanks for tuning in.